You're sitting still right now, but actually you're spinning at about 140 miles per hour on a planet that's hurtling through space at 67,000 miles per hour around a star that's racing through the galaxy at around 514,000 miles per hour. And you feel nothing. So here's the question that breaks most people's brains. What would happen if you could somehow travel at the speed of light, about 670 million miles per hour? The answer isn't just that you'd get somewhere fast. The answer is that you'd break reality itself. And the strangest part isn't what would happen to the universe around you, it's what would happen to you. Let's start with what the speed of light actually is, because most people think about it completely wrong. The speed of light isn't just really fast. Well, it's 299,792,158 meters per second. That's fast enough to circle the Earth more than 7 times in 1 second. Now here's what changes everything. You have mass. Your body, your clothes, even the air in your lungs, it all has mass. And here's the fundamental rule that governs our universe. Anything with mass cannot reach the speed of light. Why not? Think of it like this. Imagine you're trying to push a shopping cart up a hill that gets steeper with every step. At first it's easy, then it gets harder, then impossibly hard. Then the hill becomes so steep that no amount of force could push the cart another inch. That's what happens when you try to accelerate something with mass toward light speed, except the hill is the energy required, and it becomes infinitely steep right at light speed. But let's imagine for a moment that somehow, magically, you could approach the speed of light. What would actually happen to your body? To understand this, we need to grasp 3 concepts that Einstein figured out in 1905, concepts that completely shatter our everyday experience of reality. First, time is not the same for everyone. Your brain rebels against this idea because time feels rock-solid constant to you. Your watch ticks at the same rate whether you're sitting on your couch or driving on the highway. But that's only because you're moving incredibly slowly compared to light speed. Time actually stretches and compresses depending on how fast you're moving through space. Second, space itself can stretch and compress. I know this sounds impossible, but it's been measured thousands of times. The faster you go, the more space contracts in the direction you're traveling. Third, as you go faster, you become harder and harder to speed up, like you're getting more massive, even though you're not gaining weight. Imagine you're in the ultimate spacecraft, one that can somehow accelerate you toward light speed without killing you. Let's walk through exactly what would happen step by step. First, you'd need to accelerate. And this is where things get immediately dangerous. Your body can handle about 4 to 6 times Earth's gravity for short periods. Fighter pilots experience this during tight turns, but to reach even 1% of light speed in a reasonable time, you'd need acceleration forces that would literally squeeze the blood out of your arms and legs and into your core. Your heart couldn't pump blood to your brain, you'd pass out, and if the acceleration continued, you'd die. But let's say we solve that problem with some magical gentle acceleration that takes a full year to get you up to 99% of light speed. During that year of acceleration, something very strange would start happening to time around you. This is where reality gets genuinely weird. Imagine you have a twin who stays on Earth. As you accelerate away from Earth, time starts moving differently for you compared to your twin. It's not that your clocks break. From your perspective, everything seems totally normal. Your watch ticks normally, you age normally, you think normally. But compared to your twin on Earth, your time slows down. Think of it like 2 identical movies playing side by side. One plays at normal speed, one plays in slow motion. But if you're a character inside the slow motion movie, you don't feel slow. Your movie feels completely normal to you. It's only when someone compares the 2 movies that they can see one is running slower than the other. At 90% of light speed, if you experience 1 year, your twin on Earth experiences about 2 1/3 years. At 99% of light speed, the difference becomes dramatic. 1 year for you equals about 7 years for your twin. At 99.9% of light speed, 1 year for you equals about 22 years for your twin. And this is the part that really challenges everything you think you know. You don't feel time moving slowly. To you, everything is completely normal. It's only when you compare your experience to someone moving at a different speed that the difference becomes apparent. Now let's talk about what you'd actually see during this journey. As you approach light speed, your vision would change in bizarre ways. You know how when you're driving through snow at night, the snowflakes seem to streak toward your windshield from one point ahead of you? Light does something similar. Light from stars in front of you would get compressed into a narrow tunnel directly ahead. Everything else would fade into darkness. The light itself would shift color. Stars ahead would appear blue-white from being compressed, while any light from behind would shift red and eventually disappear entirely. Space itself would appear to contract in front of you. Distances that seemed vast when you started your journey would appear to shrink. A trip to a star 4 light-years away might appear to take only a few months from your perspective, even though observers on Earth would measure your journey as taking just over 4 years. But this is where the physics gets really strange, and where our thought experiment starts breaking down. Remember that shopping cart analogy? Let me give you the actual numbers so you can see how impossible this gets. The energy required to accelerate you increases exponentially as you approach light speed. It's like trying to fill a bucket that gets bigger every time you pour water in it. At 90% of light speed, you'd need about 2.3 times more energy to go faster than when you started from zero. At 99%, you'd need 7 times more energy. At 99.9%, you'd need 22 times more energy. But this is the kicker. To go from 99% to 99.9% of light speed requires more energy than it took to get from 0 to 99%. To go from 99.9% to 99.99% requires even more energy than all the previous acceleration combined. This is why physicists say it would take infinite energy to accelerate anything with mass to exactly light speed. The energy requirement approaches infinity, meaning you'd need more energy than exists in the entire universe. It's not just practically impossible, it's meaningless to even ask the question. But let's push our thought experiment even further and ask, what if you could somehow reach exactly light speed? This is where things get really strange. At light speed, time dilation becomes infinite. From the perspective of someone watching you, time would stop for you completely. You'd be frozen in that moment forever. But from your perspective, well, that's where the physics breaks down entirely. There is no your perspective at light speed if you have mass. Only massless particles like photons can travel at light speed. And this will completely change how you think about light. A photon that travels from the most distant galaxy to your eye, a journey that takes billions of years from our perspective, experiences no time at all. If a photon could think, it would experience being created and absorbed in the same instant, no matter how far it travels. Another complication that science fiction usually ignores: what happens when you want to stop? All that kinetic energy has to go somewhere. If you're traveling at near light speed and you hit even a speck of dust, the collision would release more energy than a nuclear bomb. The sparse gas and dust between stars would become a deadly radiation field that would kill you instantly. And speaking of radiation, at these speeds, even the gentle background radiation left over from the Big Bang would transform into deadly gamma rays. The universe itself would become hostile to your existence. So why does any of this matter to you sitting there, never likely to travel faster than a few hundred miles per hour? Because these aren't just abstract physics concepts, they're fundamental truths about reality that are affecting your life right now in ways you probably don't realize. Right now, at this very moment, there are satellites above your head that have to account for the fact that time moves differently for them than it does for you. Every GPS satellite orbiting Earth experiences time slightly faster than you do, about 38 microseconds per day faster, because they're moving fast and experiencing slightly less gravity. That might not sound like much, but GPS needs to be accurate to within a few feet. Without correcting for this time difference, your GPS would be off by several miles after just one day. Every time you use your phone to navigate, you're relying on Einstein's equations about the speed of light. The speed of light also sets the ultimate limit on how fast information can travel. When you're video chatting with someone on the other side of the planet, there's a minimum delay based on the speed of light. When NASA communicates with rovers on Mars, there's a delay of between 4 and 24 minutes depending on where Mars is in its orbit. This isn't a technological limitation, it's the universe's speed limit for cause and effect. But perhaps most importantly, understanding these concepts changes how you think about time itself. Time isn't the steady, universal constant we experience in daily life. It's flexible, relative, and depends entirely on your frame of reference. The now that you're experiencing is not the same now as someone moving at a different speed relative to you. This has profound implications for how we think about simultaneity and causality. Events that appear to happen at the same time for you might happen in a different order for someone moving very fast relative to you. The speed of light doesn't just limit how fast things can move, it limits how fast cause and effect can propagate through the universe. Even in your everyday life, you're constantly experiencing tiny relativistic effects. When you drive your car, time moves slightly slower for you than for someone standing still. The effect is so small, and we're talking about nanoseconds over your entire lifetime, that it's completely undetectable without atomic clocks. But it's real. So what would happen if you traveled at the speed of light? The honest answer is, you can't, and the question itself breaks the laws of physics. But asking it teaches us something profound about the universe we live in. Time isn't constant, space isn't fixed, and mass and energy are the same thing. The speed of light isn't just a speed limit, it's the rate at which cause and effect propagate through the fabric of spacetime itself. The next time you turn on a light switch, remember, those photons hitting your eyes experience no journey at all from the bulb to your retina. From their perspective, they were created and absorbed in the same timeless instant. And the next time you look up at the stars, remember that the light hitting your eyes left those stars years or centuries ago, carrying information about events that happened in what we call the past, but which for the photons themselves is happening right now. In a universe where time is relative and the speed of light is absolute, now is far stranger than we ever imagined.